In this example, we analyze the problem of estimating a rate or proportion, for example, the proportion of successes. To this end, the experiment is repeated n times and the number of successes k is observed. We will consider two cases. In the first, we assume that n is known, and in the second, it is assumed to be unknown, but the same for all repetitions of the experiment. In both cases, we look for a density, that is, we consider that some point of confidence interval is not sufficient. In this example, we try to estimate a rate theta, that is the proportion of values satisfying a given condition. We assume that the prior of theta is non-informative, that is uniform in the range 0, 1, which is equivalent to assume that it is a beta with parameters 1, 1, random variable. It is with these parameters. We force open bugs to generate the prior and the posterior predictives for a new experiment when the sample size is n. This means that the theoretical random number of successes k is given by a binomial random variable. Finally, we assume that we observe 9 successes of a total of m equal to 10 trials, which is our observation data. In this transparency, we have the commands for the rate example. First, the model. Our model is that the parameter theta is a beta distribution. This is the prior of our theta. And then we have the data. The number of observation k is a binomial random variable with parameters theta and n. And because we observe 9 of n equal to 10, we need to give this information. We write below the predictive distribution. You need to differentiate between the prior predictive and the posterior predictive. It is interesting to see that the prior, for the prior we use prior theta, but for the posterior we use theta. And look that when we define the data for the sample, we include theta, that is the parameter we use in the posterior, not in the prior. So this is because we want to reproduce the prior and the posterior. This is the doodle model for this case, in which you have two parts, the right part and the left part of the plot. In the right part, we have the prior, there is no sample there, but in the right, we have k, which is the sample, so that the predicted posterior theta parameter is influenced by the experimentation. However, in the case of the prior theta has no relation with the sample. We use the OpenBug software, and then here you have the plots for the prior, theta, and the posterior. In the prior, we have assumed a uniform, and then you can see on the left-hand side the uniform, but after using the sample, we have a different posterior, which is the density that is plotted on the other side. And the same is true for the other posterior. We can use the default plots provided by OpenBugs, or we can plot the different plots with MATLAB. And this is what we have done here. You can see several densities which correspond to different chains. So we can compare and see how the results change when we change the initial values. And then you can have this information. In the case of n unknown, we have the following. We assume as before that the prior theta is uniform in the range 0, 1, which is equivalent to assume the beta 1, 1 random variables, and we force OpenBugs to generate the prior and the posterior predictives for a new experiment when the sample size is n. This means that the theoretical random number of successes, k, is given by a binomial random variable. Finally, we assume that we observe 16, 18, 22, 15, and 27 successes when we repeat the experiment 5 times, which is the observation data. In this case, the model commands are given in this transparency, and you can see that the commands have different parts. First, we have the categorical probabilities, that is the prior density. In this case, n is not known, and then we assume that n is less than n max. N max is considered in this sample 500 because we have no idea of the sample size. And next we write the sample expression, which is a binomial random variable with parameters theta and n. The theta is the parameter that you use in the posterior predictive, and then we have to use another parameter, which is prior theta, as before, for the prior. And then we finish with the distribution of the prior distribution of theta, which is a uniform, and of n, which is a categorical the probability. And the same for the prior theta and the prior n. This is the doodle result for this case, and as before, you have the right-hand side and the left-hand side. In the right-hand side, you have all the information that is required for the prior predictive, and on the left-hand side, you include the sample data, the k of I, so that the predictive posterior include that information. You run the OpenBAC software, and this is what we get. You can see here the prior, posterior, and predictive densities, which is interesting to see that we can answer with densities, and we can work with densities. For example, the prior density, the predictive prior is very strange because we have no idea about the sample size, and we have assumed a maximum sample size of 500, and that is why you get this density on the upper right plot. However, below that plot there is the posterior, and then you can see that the sample size is estimated very well, even though it is not given. It is interesting to see that you can discover the dependencies of the n and theta parameters, and that is because there is a hyperbolic relation between theta and n that ranges between 16 and 27, and also with the plot, our plot, that correspond to the 0, 1 normalized values of the sample, we can have an idea of which parameters are dependent and which ones are not dependent. This is the end of this lesson that shows you how to estimate a rate or proportion by means of a density or a very large sample. Note that this goes further from a point estimate or a confidence interval and implies a new paradigm. If you want to move from point or confidence interval estimates to better estimates, you should incorporate the new methods in your daily work.